Is 35. Same question. In 35 we have h of x, which is 1 over 2x minus 3. So we want to find f comp g. G of x will be the inner and f of x will be the outer. Inner, outer. So let's decompose this function to see how they created it. And there is more than one correct answer. What will you consider as the first function that you will evaluate? Excellent. So the first function is 2x minus 3. Once I get a number here, which function do I apply to this number? Which one? 1 over x. Do we need another example? Okay, very good. 33. H of x equals the square root of x plus 5 plus 2. Again, we can have more than one correct answer. So I want an inner and I want an outer. That's fine. That's one option. Very good. As I said, there is more than one correct answer. Another answer would be, I would consider x plus 5. G of x will be x plus 5, and f of x will be exactly the square of x plus 2. Of course, there are other options. Any questions on algebra functions, function composition, and decomposing? Yes, please.
Yeah, I was wondering if you got the x from for the x plus 2 for the x of x.
Yeah, these are two different options.
Yeah, that's
so these two go together and these two go together and they will create the same function. Better?
Can we just do one more?
Yes. You want to choose? Okay, I will choose then. Let's say 27. And we have uppercase f of x, which is 9x squared plus 2. I need an inner and an outer. Of course, there is more than one correct answer. So g of x is the inner, f of x is the outer, because I'm using f comp g. If you're using g comp f, then f will be your inner. So
would g of x be 9x squared?
That's good.
And then the next one will be x plus 2.
Any questions? Very good. Now the next section deals with inverse functions. So 12.2. Before we talk about an inverse function, I have to go back 2 months ago when we started chapter 8. Okay? So I can't talk about inverse functions just now. I just have to review a few things before I get to inverse functions. Now, remember when we define the function, we said this. So let's look at the first option. Is this a function? Can anyone explain why is this a function? So every x has only one y, only one. Good. Function indeed. What about example 2? Right, every x has only one y. Second one is a function as well. What about example 3? Is example 3 a function? Not a function. It's what's called relation. Exists. It exists, but it's not a function. So it doesn't serve any purpose now. It's not important to us now. Okay, I'm coming back to these two options that were functions. Okay. One has a wonderful property that the other one does not. So now look at this and imagine that these are the x values and you want to go backwards. You'll go back from here to here. You're going to back here from here to here. You're going to go back here from here to the here and from here to here. Is the expression going backwards or the method going backwards also a function? So this function has a special property that it's called one-to-one. To each y, only one x. Not just to each x, only one y, but to each y, only one x. So this function number 1, is 1-to-1. Which means that its inverse will also be a function. So a function from example 1, this one, is 1-to-1 because each y value corresponds to only one x value. Therefore, going backwards, this will also be a function. So it is 1-to-1. It means that its inverse will also be a function. Its inverse is denoted by f inverse. I don't want to write like this. I don't want to confuse you. F to -1. But we don't read it f to -1. It's f inverse. F inverse.
Did I say its inverse B?
Its inverse is, sorry about that, is denoted by f to the power -1 of x. But we don't read it like that. It's not 1/f. We know that 5 to -1 is 1/5. This is not that. We do not apply such a property to f inverse. This just means is the inverse function of function f. Coming back to the second example. If I want to create a function going backwards, will this be a function? No, because this value will go back to two different y values. This x will go back to two different y values. So this is a function. However, it is not, it's not 1-to-1. So in number 2, this is number 2, I will have to write 2 is a function, comma, but not 1-to-1, comma, therefore, or colon, therefore, it does not have an inverse function. So example number 2 is a function, but not 1-to-1. Therefore, it does not have an inverse function. Okay. So coming back to the definition of an inverse function, first of all, a function must be one-to-one in order to have an inverse. How I determine the inverse, I'll explain in a minute. How we determine the domain and the range of the inverse, I'll explain in a minute. So, well, let's say I am given some graphs now. This is one graph. This is a very well-known graph so far. Can anyone tell us which graph I'm graphing here? This we don't know because we have not graphed something like this, but we graph this. Very good, the cube root of x. Then I'm going to ask you, what is this? Which we graphed a lot. Very good, excellent. And I'm going to choose one more. This one. Can anyone explain us which function is this? Good. And since we are here, let's mention all functions we know. Which one I did not graph yet? Thank you so much. Thank you. Thank you. Thank you. Excellent. So now I'm given these graphs and I'm asked, identify which one is one-to-one. Is the first one one-to-one? For a particular y value, I have to get only one x value. But look how many values I get. So this is basically this. For y equals 1, I get 3 different values of x. Is this function one-to-one? Will it have an inverse function? No. So I'll say not one-to-one. What about this function? Is this function one-to-one? It is one-to-one. Will it have an inverse function? By the horizontal line test. By the horizontal line test. What was the vertical line test all about? What did we establish with the vertical line test? Whether a graph represented a function or not. That was by the vertical line test. The horizontal line test, it tells us whether the function is one-to-one or not. Okay, what can you say about x squared? Not one-to-one. It's a function by the vertical line test, but by the horizontal line test is not one-to-one. What can you tell me about the square root? Is the square root? Yes, by the horizontal line test is one-to-one. What can you say about the absolute value? Is it one-to-one? No, not one-to-one. Good. Let's establish how we determine whether a function is, how we determine the inverse function. Okay. Can anyone give us a function that is one-to-one? Wonderful. Excellent. The cube root of a function, please. I'm going to say x minus 9. Perfect. Excellent. So I am given a function. We know, because we know the graph, it's going to be shifted where? Which direction? Wonderful, because 9 minus 9 is 0. Right, excellent. So, but we know, we pictured the graph and we know it's one-to-one, correct? Okay. Find its, so it's one-to-one. Find its F inverse. This is red, F inverse. Step 1. Replace f of x with y. Am I allowed to do that? Are these two, f of x and y, are they the same? Of course they are the same. Good. So then I write y equals the cube root of x minus 9. Excellent. In step 2, I'm going to interchange or swap x and y. Wait a minute. How can I do that? What allows me to replace x with y and y with x? Here's what allows me to. Coming back to our graph, to our bubble here. This is x for f. This point, this value is y for f. But I want to go backwards. What will these previous y values will become for the function I'm looking for? They will become x. That's the reason why I'm allowed to change the y into x. Okay, perfect. So when I interchange x with y, I'm going to write x equals the cube root of y minus 9. In step 3, I'm going to solve for y. And since we went through chapter 10, you will tell me how to solve this equation for y. What should I do to get y? No, I have to solve for y. What will you tell me to do? Chapter 10. How do I solve for y? Of course. I have to cube the left-hand side. I have to cube the right-hand side. Of course. I need to eliminate what's in the way. So the left-hand side is x cubed and the right-hand side is? Of course. So finally, what should I do to get y by itself? Good. So x cubed plus 9. Step 4, I write f inverse equals, can anyone tell us? What is f inverse? That's it. X cubed plus 9 indeed. This is it. This is the procedure. Yes?
Did you just switch it without the operation on it?
You mean from here?
No, bottom one.
From here?
Yeah.
Yeah, all I have to do is just replace y by f inverse. And I copied the rest. Yep.
So swap it back basically.
No, this y is a totally different function. It's f inverse. We started with this function, which was y. Now this y is f inverse. They are totally different. Totally different. Okay, so I like to, this is not done. I still have a few things, but I would like to find more inverses now. On page 728. Problem 33. 728. Problem 33. Okay. F of x equals x minus 2 over 5. They told us that this function is 1-to-1. What type of function is it? It can be rewritten like this. X over 5 minus 2 over 5. What type of function is this? A number times x minus a number. What is its degree? If I know its degree, I'll know what it is. Linear. It's a linear function with a positive slope. Imagine the graph and tell me whether it's 1-to-1. It is. So we agree that this is indeed linear and it's 1-to-1. All linear functions, obviously 1-to-1. Good. Can anyone dictate the first step? We need to find its inverse. Excellent. That's the first step. So then y equals x minus 2 over 5. In step 2, what do I do in step 2? Good. I'm allowed to do that because I'm looking for the inverse. And now y, the new y will be the inverse. Good. What should I do next? Good. How do I do that? Excellent. 5x equals y minus 2. Good. So y equals 5x plus 2. And in step 4, I'm done. But I have to state that f inverse equals. Good. I'm going to add something here. Any questions? I'm going to add something here. Graph f of x and its inverse on the same coordinate system. Okay. Which function would you like to graph first? Good. So f of x was 1/5 x minus 2/5. Or if you want, if it's better, y equals 1/5 x minus 2/5, and I will multiply both sides by 5. So then 5x equals x minus 2. 5y equals x minus 2. Okay, it's linear. So when x is 0, how much is y? -2/5. So 0, -2/5, which we knew from the beginning. That's the y-intercept. And now when y is 0, how much is x? Very good. So I have 2, 0. So I found the x and y intercepts. I made x equals 0, I found the y. I made y equals 0, I found the x. Good. So can anyone dictate? I know I see them right in front of me, but I just want to make sure we know what we are plotting. What are we plotting now? I'm going to plot in red. Comma, -2/5, which is -0.4, right? If this is, I'm going to take a big unit. If this is -1, -0.4 will be somewhere here. And then 2, 0. And here's the line, correct? Okay. I'm going to connect and extend the line. And this is the function f of x equals x minus 2/5. Now, can anyone give us two ordered pairs that we need to plot in order to graph the inverse function? Comma. Indeed. All I have to do is reverse the coordinates. Because if function f goes from 2 to 0, its inverse will be applied to 0 and will return 2. So then, that's 1, 0, 2. And can anyone give us the other one? Good. So if this is -1, somewhere here I will have -0.4. So here is f inverse, which is 5x plus 2. I was looking for it. What do you notice? Let me show you something. See, I couldn't have done that with the board, right? I folded my graph on this line that bisects, divides the first quadrant in half, and continues to bisect or divide the third quadrant in half. And look what happened. This portion of one line or one graph overlaps here, and this portion overlaps with this. What happens is that exactly they are symmetric with respect to this line, which is y equals x. Always. This always happens when you graph the function and its inverse. I'm going to write it as an important note. When graphing the function and its inverse on the same Cartesian system, you see that they are symmetric with respect to the line y equals x. This point here, where the inverse or the function crosses y equals x, is like, let's say, -2, -2. It's not, but it's on y equals x. So x and y are the same. So when I flip them, it's still the same point. So if it's negative, it's not. But if it's -1, -1, then when I flip it, it's still -1, -1. So that point where the function crosses y equals x must be part of the inverse function as well. So let's write it as a very important note. The graphs of f and f inverse, note, the graphs of f of x and f inverse for any function are always symmetric with respect to the line y equals x. Always. They're always symmetric with respect to the line y equals x. Any questions? Okay, I would like to also look at 28. F of x equals -1/2 x plus 2. I want you to find the inverse function, but let's make a statement. Is this function 1-to-1? Why? Yes. So I'm going to have to write that. F of x is 1-to-1 since it is a linear function. So in second step, I'm asked to find its inverse. Let me know if you need help. And in third step, we will have to graph the function and its inverse on the same coordinate system. What will we show? That the two graphs will be symmetric with respect to the line, because we are only reversing the order of the points. Do we need more time? Okay, in step 1. Perfect. Step 2. Excellent. Excellent. Step 3. I will multiply both sides by 2 or negative 2 just to get rid of fractions. So I have 2x equals plus 4. And this is what I would do now. I would move y and I will move 2x. It's up to you. Whatever you do, we're going to get the same answer. So then y equals negative 2x plus 4. Do you agree with that? And the final and the fourth step is f inverse of x, yes, is negative 2x plus 4. Perfect. So let's graph the inverse. When x is 0, y is? Let's graph the inverse. When x is 0, y is 4. So the ordered pair is 0, 4. When y is 0, this is 0. I suggest move negative 2x to this side. Very good. And x equals 2. So then 2 comma 0. So I'm graphing the inverse. I'm going to graph it in red. 0 comma 4. 1, 2, 3, 4. 2 comma 0. 1, 2. So this is the inverse function. Now you see how important I asked you all the time to graph and then write next to it what it is. So this is the inverse function, which is negative 2x plus 4. I don't have to do the same thing for f inverse. I'm going to graph it in green. But tell me what points to plot. And remember, the graph has to be symmetric. I never use the yellow. Let me see if anyone can see. Nobody can see anything. So remember, y equals x. So here is the inverse function. They have to cross. When the red graph crosses y equals x, the green graph has to cross at the same point because the coordinates are the same there. So this is the function, which is negative 1/2 x plus 2. And yes, you can fold this graph. This is symmetric here, and this is symmetric here. Any questions? Any questions? Now I would like to talk about a very important property. And this is the end of 12.2. Very important property. It's called the property of inverse functions. First of all, what does this mean? Only two functions that are inverses of each other have this property that I'm going to present in a minute. If two functions are not inverses of each other, they do not have this property. They do not enjoy this property. Okay? Okay. Now, here's a function that I want to create. You have X numbers of dollars in your pocket. You have X. And I'm giving you 5. What do you have right now? You have X plus 5, correct? 5 minutes later, I come back and say, give me my $5 back. Correct. Are these two functions inverses of each other? Adding 5 and subtracting 5. Are they inverses of each other? Yes, right? So you can say that f of x equals x plus 5 and g of x equals x minus 5 are inverses of each other. Can you say that? Because they cancel their effect on x. So when I give you $5, I'm using x plus 5. When I take it back from you, I'm using x minus 5. How much are you left with? Right, nothing happened to x. So if I apply the two inverse functions on x in any sequence, I take 5 from you and I give you 5 back, you still have x. So what should the function composition be if two functions are inverses of each other? If two functions are inverses of each other, then I want you to tell me what will be the function composition of those two functions. What will equal to? In any direction. F come G, and the other direction G come F. I'm giving you 5 and I'm taking it back. What are you left with when I applied two functions? I applied the function by adding you 5, and I came around and I said, I'm applying the function of taking 5 back. What are you left with? Indeed, x. This is the property of inverse functions. Not x squared. If I get x squared, those two functions are not inverses of each other. If I get x over 3, those two functions are not inverses of each other. Only if I apply f and I apply g and nothing happens to x, and if I apply g and then I apply f, nothing happens to x, only then these two functions are inverses of each other. Okay, on page I don't have examples in the book, so I have to make one up. This is a very important property. So I'm going to say f of x equals x minus 1 over 2, and g of x equals 2x plus 1. The question here is, are these inverses of each other? Are f of x and g of x inverses of each other? And you can not say yay or nay. You have to say, give me a minute. I will find f come g. And then give me another minute. I will find g come f. And only if this one will result into, and this one will result into, then I will conclude for sure that these two functions are or are not inverses of each other. Right? Otherwise, I will never get x. If these two functions are not inverses of each other, I will never get plain x. Good. So let's determine f come g. From the previous section, f of g of x, which is 2x plus 1 minus 1 over 2. I simplify, I get 2x over 2. I simplify again, and I get x. Now I have to find g comp f of x, which is g of x minus 1 over 2, which is 2 multiplied by minus 1 over 2 and plus 1. I simplify these two. I get x minus 1 plus 1, and the answer is only in this situation and no other. I can say, yeah, because I apply two different functions in any order, and I still got plain x, which means one canceled its effect, the effect on the other on x. Okay? Any questions? Any questions? Any questions? Should we work on another example? Perfect. Okay, so let me choose another. Let's say f of x equals x to the third plus 6, and g of x equals the cube root of x minus 6. We're asked to show whether they are or they are not inverses of each other. What do I have to show? I have to find, very good, I have to find f cum g, which is indeed f of g of x. And I also have, what if I get here 5x? Do I have to determine g cum f if I get 5x for the first one? No. I don't care if the other one even is x. It's not going to be, but even if it is, I don't care, because the first one is not x. So this will be f of the cube root of x minus 6. So this will be the cube root of x minus 6 cubed plus 6. How much is the cube root of x minus 6 cubed? And now the other one, g cum f, is g of f of x, which is g of, very good. And now I look at g, and g says the cube root of whatever minus 6. So, oh, I forgot to write here the result. F and g are inverses of each other. Same thing here. These two, f and g, are inverses of each other. Any questions? So as a quick summary, we know that functions can be one-to-one or not. If they are one-to-one, that's a great property because it means that they have inverse functions. I know how to find the inverse function of a one-to-one function with a 4-step procedure. And I also know that when I graph the function and its inverse on the same Cartesian system or coordinate system, the graphs will be symmetric with respect to the line y equals x. I also know that two functions are inverses of each other if they cancel their effect. One cancels the effect of the other on x. This being said, I just want to start 12.3, which is exponential functions. We're not going to graph it today. I just want to talk for a few minutes and then I'll stop about the exponential function. Why do you think that this function is called the square root? Because it has a square root. What do you think that this function is called? Because it has. Why do you think this function is called exponential? Right. The variable is the exponent. So f of x equals the base to an exponent. This is a fixed number. Fixed number. That's not a variable. It's a number raised to x. That's why this is called the exponential function, because the exponent is the variable. Now, there are some problems here with the base. So a is the base. And here's just a quick question for you. Can I raise negative 3 to the second power? Of course I can, and I get? Good. Can I raise 0 to the third power? Of course I can, and I get 0. Can I raise 1 to the fifth power? Yes, and I get 1. However, the base of the exponential function cannot be a negative number, cannot be 0, and cannot be 1. So there are only two options for a, which is the base. I'm not talking about the exponent. The exponent can be anything. The base itself can either be between 0 and 1, not 0 and not 1. Notice that I use parentheses. Or it can be between 1 and infinity, not 1. So there will be two shapes. As an example, for this situation, I will have, let's say, 1/2 to the x, 1/3 to the x, 1/16 to the x, 1/5, 1/5 to the x, and so on and so forth. For this, as an example, I will have, let's say, 3 to the x. Let's say I'll have 10 to the x, and so on and so forth. So this function has a lot of applicability in real-life situations. When you'll get your mortgage, when you buy a house or you buy a car, the monthly rate is calculated using an exponential function. They will calculate and tell you you have to pay $250 a month, and that involves an exponential function. Bacteria grow exponentially. Populations in general, assuming they grow. I don't want to say decrease. So if they have a negative exponential growth, then they will decrease. But they increase over time. Mice, rabbits grow exponentially. What are examples I can give you with the exponential function? The logistic function, which is another exponential function, it has exponential function in it, is another example. So this has a lot of applicability. This function and its inverse. I'll stop here for today. We will continue with 12.3 and the rest.